This video will be about the E2 mechanism. I'll give an overview of the reaction mechanism, and then we'll also discuss kinetics. So E2 is of the class of reactions called eliminations, which overall look like this, where we have X and Y, where often X or Y, one of the two will be a hydrogen atom, and we usually have a base as the other reagent. And in the final product, we have an alkene, or we've created a new pi bond. So if we start with an alkane, we end up with an alkene. If we start out with an alkene, then we'll end up with an alkyne. We also have the conjugate base, and we have the leaving group, which will often be an anion, but sometimes can be neutral. So this is the overall class of reactions. The E2 specifically is bimolecular elimination. And what this means is that there are two molecules involved in the rate determining step. RDS, rate determining step. For E2, that means that there's just going to be one step in the mechanism. It's going to be a concerted mechanism. And we'll talk more about the stereochemistry in another video, but this one is stereospecific. So for some molecules, that will mean you will get a particular outcome. So the mechanism for the E2, since it is bimolecular, is that the base and the substrate are together in that mechanistic step. So let's take a look at the mechanism. So the base goes and attacks the proton. So this would be the alpha carbon, and this is the beta carbon. That's another thing I wanted to point out. The alpha carbon is the one attached to the leaving group. And then the beta carbon is the one that the proton gets removed from. Now in this particular example, I'm only showing two carbon atoms, so there's only one choice here for the beta carbon. And we're going to have to take a hydrogen atom from that carbon atom. Later we'll talk about what's called regioselectivity, which is sometimes we'll have substrates where we have to decide where to remove the proton, what's going to be the most probable outcome in terms of where does the pi bond go. So that pi bond gets made using the carbon-hydrogen bond electrons, and at the same time, the leaving group leaves. So all three arrows, so notice that this is three arrows, these are all occurring simultaneously. It's not that the base grabs the proton and then the pi bond forms and then the leaving group leaves. This is all happening all at once. So now we end up with the alkene. If it helps, you can draw out the other hydrogen atoms here just to remind you what is bound here, so that you don't add or subtract any carbon atoms accidentally. And then we're going to have the conjugate acid. Here, since we started with an alkane, we're going to end up with an alkene. And one thing I need to add up here that I didn't state explicitly is that elimination reactions are going to be where a new pi bond forms. And the way that that pi bond forms is that we're eliminating these two groups from the structure, and then we're able to form the pi bond. And then we also have the leaving group, which in this case I've represented with the letter Y. So just like, and this one would be an anion because this was neutral here. It is possible to have the leaving group be neutral depending upon, you know, what it is you're starting with. So for the kinetics here, the equation is actually going to look exactly like the SN2 equation, except that instead of acting as a nucleophile, we're going to have a base as our other reagent. So this is the rate determining step. It's the only step in the E2 mechanism. And so that means the rate is going to be equal to the rate constant, which would have to be determined experimentally, times the concentration of the substrate, times the concentration of the base. So that means if I were to double the concentration of the base, I double the rate. If I double the concentration of the substrate, I double the rate, and so on and so forth. That's it for now. I'll have another video on regiochemistry, on the stereochemistry, and then what makes the E2 mechanism be favored.